Hi students, welcome to this video module on the topic electromagnetic waves in conductors. In the previous video modules, we learned about electromagnetic waves in free space or in matter like glass, dielectric materials like glass, water, etc. So in such materials or either in vacuum or in a dielectric medium, we can treat the free charge density or free currents as zero. But that is not the matter in case of conductors. In case of conductors, there will be a free charge density rho f and a free current density jf, which is not there in the case of uh, electromagnetic waves in vacuum. So the difference in the case of conductors is the presence of these free charges and free currents. So we know that the free currents using the Ohm's law, Jf is equal to sigma E. And we learned Maxwell's equations. Del dot E is equal to 1 divided by epsilon 0 times rho. Del dot B equal to 0. Del cross E equal to minus dou B by dou T. Del cross B is equal to mu 0 J plus mu 0 epsilon 0 dou E by dou T. But when it comes to the case of matter, epsilon 0 can be replaced by epsilon. Mu 0 can be replaced by mu. Okay, and using Jf equal to sigma E, we can and the case of free charges also, for conductors we can write the Maxwell's equations in a linear media. It takes the form del dot E equal to 1 by epsilon rho f del cross del dot B equal to 0, del cross E equal to minus dou B by dou T, and del cross B equal to mu sigma E. Why? That is actually, it was mu 0 Jf. So instead of J, we substituted sigma E. This is actually J. Okay. Plus mu epsilon dou E by dou T. So for the case of conductors, we included rho f and Jf, and Jf equal to sigma E from Ohm's law. So the fourth and the first one changed. The fourth and the first Maxwell's equations got a small changes like this. Okay. So this is the Maxwell's equations for conducting media that we already wrote. Now we can write the continuity equation for free charge. Del dot J equal to minus dou rho by dou T. Here it will become minus dou rho F by dou T. So using this and the Ohm's law and Gauss law, we can write dou rho by dou T, dou rho F by dou T is equal to, it is del dot Jf. Since of Jf, we can substitute sigma E, and that is a negative sign because del dot J is equal to minus dou rho by dou T. So I'm just taking dou rho by dou T is equal to minus del dot J, and del dot J can be replaced by sigma E. Now, slight rearrangement. This can be minus sigma into del dot E. But we know from the first Maxwell equation or Gauss law, we can substitute this as minus sigma divided by epsilon times rho F. So dou rho by dou T is equal to minus sigma by epsilon times rho F. And for a homogeneous linear conducting medium, we can write this rho F at any time t is equal to e to the power minus sigma by epsilon t rho F of 0. Rho f of 0 is the initial free charge density, and rho f of t is the charge density after a time t. And sigma, epsilon by sigma, is called the characteristic time. Tau is equal to epsilon divided by sigma. That is the factor that we used here. So it is actually like a time constant. So for this time constant signifies how good a conductor is. So for a perfect conductor, the sigma value will be infinity and the time constant will be 0. And for a good conductor, the tau is much less than 1 by omega other times. And for a poor conductor, tau is very much greater than 1 by omega. So what is actually a perfect what is actually a perfect conductor or a good conductor and an insulator? That can be classified based on this characteristic time or time constant tau, which is equal to epsilon divided by sigma. This shows if you put some free charges on a conductor, it will flow out to the edges. If you keep some free charges, that instant it moves to the surface, to the edges, I mean. So how much time it takes to reach the edges, that shows how good a conductor is. So for a perfect conductor, it reaches all of a sudden when you keep that charge. That means time constant is 0. That is for a perfect thing. And for a good conductor, it takes much less time to reach the surface. And for a bad conductor, it takes infinite time. It takes much longer time to reach the surface, or it never reaches the surface. So these are the classification of materials based on this time constant. Anyway, so we are not concerned here, or we are not interested in this transient behavior, but we will wait for any accumulated charge to disappear from. That means whatever the time it takes, we'll wait for rho f to be 0, the free charges to be 0 inside that. So we know that for a conductor, whether it is very fast or by taking some time, the free charges inside will become 0 and it moves to the edges. So at some instant of time, the free charges will be 0. So we will wait till that time, and then after that we are applying, or at that moment we are just going to apply the Maxwell's equations here. Okay, see. So at that instant, when the free charges inside becomes 0, we can rewrite the Maxwell's equations into del dot E equal to 0. It was del dot E is equal to rho f by epsilon. But as we discussed now, in the case of a conductor, whether it is a perfect conductor or a good conductor, in certain time duration, the free charge inside becomes 0 as it moves to the edges. So at that instant, you can write rho f equals 0. So del dot E equal to 0. Then del dot B is already 0. Del cross E is equal to minus dou B by dou T, and del cross B equal to mu epsilon dou E by dou T plus mu sigma E. Everything as usual except the first equation. Okay, I hope this is clear. The concept of free charge. Taking the curl of the third and the fourth Maxwell's equations for conductors. So we are taking the curl of the third equation. You see, del cross E equal to del cross minus dou B by dou T. The equation was del cross E equal to minus dou B by dou T. So we took the curl on both sides. Okay, and then rearranged minus dou by the right side. I'm just rearranging the right side minus dou by dou T of del cross B. But from the fourth equation, we can substitute for del cross B. What is del cross B? It is mu epsilon dou E by dou T plus mu sigma E. Now, the right side, it is del cross E. We can write it as del of del dot E minus del square E equal to, on the right side, it is mu sigma dou square E by dou t square minus mu sigma dou E by dou t. Now, we know that from the first Maxwell equation, del dot E equal to 0. So, this first term vanishes. So, only the next three terms remains. So, minus del square E equal to minus mu epsilon dou square E by dou t square minus mu sigma dou E by dou t. We can cancel the negative from both sides. Hence, we obtain this equation, del square E equal to mu sigma, sorry, mu epsilon dou square E by dou t square plus mu sigma dou E by dou t. This is the what's called wave equation for electric field, but it's a modified form. I'll say why it's a modified form. Okay, now in the same way, you can apply the curl to fourth Maxwell's equation and simplify that. You'll reach this del square B equal to mu epsilon dou square B by dou t square plus mu sigma dou B by dou t. So hence we obtained the wave equation for electric field and the modified wave equations for electric field and magnetic field. We know that for the case of free space or dielectric, we obtained the wave equation del square E equal to mu epsilon dou square E by dou t square. But here you can see an additional term. That is why I say it's a modified term. And still, this represents the wave equation for electric field and magnetic field in the case of conductors. And this admits plane wave solutions like E equal to E0 e to the power I k complex z minus omega t. So I can write the solution of this one, E complex equal to E0 exponential I k complex z minus omega t. Here the difference from free space equation is that you can see the wave number is a complex number here. It was not like that in the case of a conductor. I mean, in the case of a free space. So I hope you remember the wave number related to frequency and speed by the equation omega by, in the case of free space, it was omega by k equal to c, that is equal to 1 by root of mu 0 epsilon 0. So when you square on both sides, for the case of free space, it was omega square mu 0 epsilon 0 equal to k square. But here you can see that k square, other than the first term, mu 0 epsilon 0 omega square, is replaced by mu epsilon omega square, plus there's an additional term, because we know the solution of this one is a complex, it is having a complex wave number. Therefore, other than the first term that we learned in case of a free space, in case of conductors, we can write k bar square is equal to mu epsilon omega square plus I mu sigma omega, which corresponds to the second term or the modified term in the wave equation. So the wave number takes the form k bar equal to k plus I kappa. You can see this second term, it is I, it is not purely k, it is kappa. This term is kappa, not k. Okay, so k bar equal to the complex wave number k bar equal to k plus I kappa. Now, let us calculate the values of k and kappa in the complex wave number k bar. We know that k bar is equal to k plus I kappa. It consists of a real part k and an imaginary part I kappa. So we have to find those real numbers k and kappa. So for that, we already introduced k bar square is equal to mu epsilon omega square plus I mu sigma omega. Let that be equation 1. Also, in the previous slide, we noticed k bar is equal to k plus I kappa. Equation number 2. Square this equation, we'll get k bar or k complex square is equal to k plus I kappa whole square. Expanding by utilizing a plus b whole square term, we know that is a square plus b square plus 2ab. So this is a square, this is b square, and the third term is 2ab. And we know that I square, the square of complex number I, it is minus 1. So k square minus kappa square, then this 2ik. So the same I 2k kappa. Okay. Now comparing this with the first equation, that is k bar square. This is k bar square. Okay, so k bar square, there are two equations, equation number 1 and equation 3, both representing the same equation. So when you compare the real part and imaginary part, you will get k square minus kappa square equal to mu epsilon omega square. And also the next part gives 2k kappa is equal to mu sigma omega. This can be rearranged. That is k equal to mu sigma omega divided by 2 kappa. So took this 2 and kappa to the other side. Let this be equation number 5. Now by substituting the value of k from equation 5 into equation 4, so you can see that equation 4 become mu square, because it is k square. So mu square sigma square omega square divided by 2k whole square, that is 4k square. I mean 4 kappa square minus kappa square equal to, on the right side, it is mu epsilon omega square here. Now rearranging this, take the 4 kappa square or as an LCM, make the common denominator. It become 4 kappa square into k square, that become 4 kappa raised to 4. Then 4 kappa square mu sigma epsilon square, that become 4 kappa square mu epsilon omega square, minus there is one mu square sigma square omega square. So you can see mu square sigma square omega square. Okay, so we got an expression like this. Now that expression, that is 4k square, sorry, 4k to the power 4 plus 4, I mean 4 kappa to the power 4 plus 4 kappa to the power square mu epsilon omega square minus mu square sigma square omega square equal to 0. This resembles a quadratic equation in kappa square. Here x equal to kappa square. So this is like ax square plus bx plus c equal to 0, where x is kappa to the power 2. And we know the solution is minus b plus 2 plus or minus root of b square minus 4az by 2a. Okay, utilizing that, kappa square, here the variable is kappa square, not kappa, it's kappa square, because it is kappa to the power 4 in this equation. Okay, so kappa square equal to minus, here b is, what is actually b? 4 mu 0 epsilon omega square. So 4 mu 0, I mean mu epsilon omega square plus or minus root of b square. So 16 mu square epsilon square omega to the power 4 minus 4az. So minus, and there is already a minus in the c term, that is why it became positive here. Then 4ac. So 4 times 4 is 16 mu square sigma square omega square by 2a. So 2 times 4. So it's 8. This can be simplified to, or you can take from the square root, you can take 16 out, it become 4. Mu square out, it become mu. Omega square, sigma square out is sigma. And omega to the power 4, you can take as a common factor. So there is no omega square in the second term. So what we can do is multiply and divide with omega square. So there is an omega square in the denominator now. And omega to the power 4 is taken as common factor. Out of square root, it will be omega square now. And there was no epsilon also in the second term. That is why we divided with epsilon square here. Now, 4 is a common factor, mu is common factor, epsilon is common factor, and omega square is also common factor. We took all these commons out, and 4 and 8 cancelled to give a 2 there. Okay. Then inside the bracket there is a minus, and here it is 1, and the last term root of 1 plus sigma square omega square epsilon square. So you'll get two terms here. One, so when you take the square root of this, that is square root of this entire term, you can find there are one a term with a minus 1 plus root of this one, and another term is minus 1 minus root of 1 plus sigma square by omega square. We know that the equation is k complex equal to k plus I kappa. So these k and kappa are actually real numbers. Because the presence of this I, it became complex number. Okay, so here you will get two answers. One answer with a root of -1 and another answer with a root of +1, and the of course other terms are there, mu epsilon omega square by 2 and everything is there. So we are eliminating this root of -1 term because it will give a complex number again, and that will lead to because we know the kappa term must be a real number. So we are taking the positive value only. So you can see that the value of kappa is root of mu epsilon omega square by 2 times root of -1 plus or -1 root of 1 plus sigma square of omega square. We're taking the real part only. So omega square root is omega. Root of mu epsilon by 2 root, it is already in here. Then there is terms like -1 minus root of 1 plus sigma square by epsilon square omega square, and -1 plus root of 1 plus sigma square by omega square epsilon, and this is under root. So this will certainly lead to a -1, and this will lead to a positive number under root. So we are taking only that one because we need a real part answer as a real number. So kappa is equal to omega times root of mu epsilon by 2 and under root of 1 plus sigma square by epsilon square omega square minus 1. So hence we got the value of kappa. Our next aim is to find the value of k. So again we are taking this equation, that is equation k square minus kappa square equal to mu epsilon omega square. In that we are going to substitute kappa square. Okay, so when you substitute kappa square, the equation becomes k square minus omega square mu epsilon by 2 root of 1 plus sigma square by epsilon square omega square minus 1 equal to, on the other side it is mu epsilon omega square. Okay, now k square equal to, you're taking this second term from left to right and taking the common factors out, because mu square mu omega square epsilon by 2 is a common factor. When you take that common factor outside, there will be, okay, there is a 2 here, so taking LCM 2 plus root of 1 plus sigma square by epsilon square omega square minus 1. Then 2 and this minus 1, it becomes 2 minus 1, so it is 1. So k is equal to omega times root of, here is actually plus or minus. Okay, so but we are taking only real part of this answer. So omega, we're taking the square root, omega square root is omega, and root of mu epsilon by 2 times root of 1 plus sigma by epsilon 0 square minus 1. We took the real part of this answer only, not the imaginary part. Okay, so hence we got the expression for k and kappa. You can see that k is equal to omega by root of mu epsilon divided by 2 times root of 1 plus sigma by epsilon omega square plus 1, and the other one is minus 1 and to the power 1 by 2. Okay, so again come back to the equations. So we can see that the complex amplitude of electric field E0 is equal to E equal to E0 complex exponential minus kappa z e to the power I k z minus omega t, because we know that the expression for electric field is this. So when you expand that, it becomes E0 complex e to the power I. It was k complex. So instead of k complex, what you can write? You can write k plus I kappa. So it becomes k z plus I kappa z minus omega t. Okay. Now expanding this, it will be E0 complex exponential I k z. Just taking I into the terms. Okay, then e to the power I times I, it become minus kappa z, then e to the power minus I omega t. I can write this as E0 complex exponential minus kappa z times, again exponential, I times k z minus omega t. So you can see that other than the normal equation, that is E complex equal to E0 e to the power I k z minus omega t, we can see an additional term there, that is e to the power minus kappa z. This exponential with a minus exponential, that shows a term with a decreasing amplitude. So and the second term e to the power I k z minus omega t, that shows the propagating or what is known as a traveling wave equation. But the term with the exponential minus, that shows a wave with a continuously decreasing amplitude. So when a wave approaches from a from free space to a conducting media, what actually happens? You can see that in free space the amplitude remains constant, but when it enter into a conducting medium, what happens? Due to the presence of this e to the power minus kappa z, the amplitude decreases continuously. You can see the decreasing amplitude. So whenever the the electromagnetic wave enter into a conducting medium, its amplitude decreases. That is shown by, or that is represented by the term e to the power minus kappa z in the electric field equation as well as in the magnetic field equation. So I hope it is clear. In the case of a conducting medium, the amplitude of electromagnetic wave continuously decreases. So here actually we can define a term called skin depth. Skin depth is this skin depth. Okay. In the previous slide I explained, till it reaches the conductor, its amplitude is constant. But when it enter into the conducting medium, what happens? Amplitude decreases. So the distance it takes to reduce the amplitude to 1 by E of the initial value is called its skin depth. It is represent, or it's equal to D equal to 1 by kappa. It is a measure of how far the wave penetrates into a conducting medium. Okay, and the real part of the complex wave number k bar is k plus I kappa. So here the real part signifies the wave parameters like wavelength, propagation speed, index of refraction, etc. And that is given by, as usual, in the case of an electromagnetic wave in a free space. Lambda is equal to pi by k, and v is omega by k, and refractive index is ck by omega. That all signifies by this real part of the wave number. The last term signifies to what extent, I mean, last term means the imaginary term, the kappa term, that signifies to what extent the wave penetrate into the medium. So D, the skin thickness or skin depth, is equal to 1 by kappa. Okay. So as usual, we can write electric field is given by E complex equal to 0 e to the power minus kappa z e to the power I k z minus omega tx, and B equal to, here you can see instead of B0, we can write as usual is k complex divided by omega E0, and the rest is same, e to the power minus k z, I mean minus kappa z e to the power I k z minus omega t. Now, like any complex number, we can write, we know that k is k complex equal to k plus I kappa. So we can write this k in terms of modulus and phase factors. Any complex number can be written as modulus term and a phase term. So k complex equal to capital K times e to the power I phi, where this capital K represents its modulus, magnitude, and phi represents a phase. So K, capital K is modulus of the complex K, that is root of, because K bar, K complex equal to K plus I kappa. So its magnitude is square root of K square plus kappa square. K square plus kappa square, and we know the values of this k and kappa, we already derived. Substituting this in the root of k square plus kappa square, you will get omega times root of epsilon mu root of 1 plus sigma by epsilon whole square. You can try this calculation. This is simply by substituting this k square and omega square, you will get this expression. Also, the value of phi. Uh, Phi is equal to, because if k is k complex equal to k plus ik, then the angle phi is equal to or tan of phi. Tan phi is equal to k complex, I mean kappa divided by k. So phi is equal to tan inverse of kappa divided by k. Okay, so this complex number has got its magnitude term as well as the phase term. Now, as per the expressions for electric field and magnetic field, we already wrote the expression for electric field is equal to E complex equal to E0 complex. Then there's an exponential minus kappa z, then exponential of I k z minus omega t. Here, this epsilon, the E complex, can be written as E0 plus I delta E. We already introduced this complex notation in the previous videos. You can, if you have some doubt in this representation of E0 complex equal E0 I delta, you can watch the previous video modules on the introduction of complex terms. Okay, and B0 equal to B0 e to the power I delta B, and B0 can be replaced by k by omega, because V0 equal to 1 by V times E0. That's why this k by omega is used, e to the power I phi, then E0 I delta E. Okay. So evidently the electric and the magnetic field. So we got the expression for electric field as well as magnetic field, and this is the electric field amplitude, complex electric field amplitude and complex magnetic field amplitude. Evidently, the electric and magnetic fields are no longer in phase. You can see these expressions, they are no longer in phase. So there is a phase difference between them because there is an additional term e raised to I phi occur there. So you can see that delta B minus delta E, they are not in phase. Del E to the power I delta E plus phi is there in case of magnetic field. So delta B minus delta E is equal to phi. So that is why delta B minus delta is equal to phi. And also B0 by E0 is equal to k by omega. And when you substitute the values of k and omega, you will get B0 by E0 equal to root of mu epsilon times root of 1 plus sigma by epsilon omega whole square. You can try these mathematics calculations if you need. Okay, because we just substituted the values. That's only happened here. Okay, now this yields the expression for electric field E is equal to E0 e to the power I. Now from the complex notations, we are going to the normal expression for electric field E equal to E0 e to the power I kz cos kz minus omega t plus delta, and B equal to B0 e to the power minus kz cos kz minus omega t plus delta plus phi. There is a phase difference between them that we obtained from delta B minus delta E. And this is e to the power I kappa z. This is e to the power I minus I kappa z. So these are the expression for electric field and magnetic field of an electromagnetic wave when it is propagating in a conducting medium. Okay. Okay, students. I hope these explanations are clear. Okay, I hope you understood how the electric and electromagnetic wave propagate in a conducting medium. When it enter from a free space to a conducting medium, what happens? Its amplitude decreases or damping starts, and that is expressed by the term e to the power minus kappa z. Okay, okay, students. Bye. Thank you.